Hi everyone. This is the recorded lecture for the 29th and 31st of August. If we were meeting in person, it would be classes 3 and 4, but instead we're going to have this recorded video lecture, and let's begin by taking a look at some announcements here. The second homework assignment, homework number 2, that is due on Thursday, September 7th, and that assignment is available right now for you to look at on MU Online. It's related to stormwater and the rational method, so it's all related to the material that's included in this lecture, and you'll notice that it's due on Thursday the 7th, and so if you have any lingering uncertainties after watching this lecture, then I'll have some time in the following week for you to come talk to me. We'll have class on Tuesday in person before the assignment is due on the 7th. So today's lecture, as it says at the bottom there, is related to stormwater control. Talking a little bit about the infrastructure for accepting stormwater in urban areas, and then also the simplest method for modeling hydrologic runoff, the rational method. And so I will mention that the bulk of this lecture was recorded on a different occasion, and so there may be some incidental references to times and dates that don't seem to make sense. You can ignore any of those things. The thing that will be consistent, though, is the material itself. The concepts haven't changed from that semester to this. And so if you have any questions, feel free to send me an email. Otherwise, I'll see you back in our live face-to-face meetings on Tuesday, September 5th.
All right, now there's a couple of pictures here that I want you to tell me, what do you think, what's your interpretation? Oh, it's not even dim enough. This is better. All right, so here's a picture. Here's one. Okay, so what do you think is the point of painting images on the street in front of an inlet like this? What do you think they're trying to let the general public know? Yeah, where the water goes, because most people don't think of it in terms of the runoff from the street, which includes any spilled gasoline, the oil that's dripping from the bottom of your car, salt that's applied to the roads in order to melt the ice. All of those contaminants are going to make their way into streams. And one thing that they've had problems with over the years is people pouring antifreeze, like old used antifreeze, when they're flushing out the radiator of their car. And that's potentially dangerous to wildlife and fish. And so all of these are trying to help people know that you're having an environmental effect, and we drink from the river as well. I think that that's what this is showing a water tap, because it's a closed cycle. It's not just some vague, the environment we're trying to protect. The environment, you can poison the environment a little bit because I'm not the environment. But when you start thinking about, well, I'm poisoning myself if I discharge bad stuff into the rivers, that's kind of what this is trying to get you to think about. And so, although we're going to be talking a lot about the quantity of runoff during this semester, there is a relationship between the amount of water that's flowing and also the quality. Because sometimes when the floodwaters get so high, they can inundate areas that were never intended to be submerged. And that was a big part of what happened during the hurricane that was in the Gulf back in 2005, Hurricane Katrina, I think it was, is that the storm surge came in parts of Louisiana that were heavily contaminated, and it sort of mixed it all up. It spread the contamination. So there's a relationship between the flow in a stream and the water quality. For the most part, though, we're going to be looking at issues of timing of water and trying to attenuate peak flows. This is showing discharge coming into a flow equalization pond. And ponds like this, sometimes you drive past them without even noticing them. They can look like maybe parks or green features. There's one by Target. If you know that area very well, there's a big runoff pond there, because there's a lot of paved area where they've got Target and Home Depot. A lot of parking lots are very highly impervious, and so there's going to be more runoff from a developed area than there was when it was raw nature and more of the water was infiltrating down into the soil. And so we have to find ways to know the correct size of ponds like this, and also understand how the timing of the water changes when you put in an engineered structure like that. So urban stormwater management is trying to control the hydrologic cycle and really the effects of the hydrologic cycle on areas that have been disturbed. When we urbanize an area, inevitably we're increasing the amount of impermeability by adding roof areas and by adding concrete walkways and paved areas. What we're doing is we're limiting the amount of water that can infiltrate to the soil and increasing how much of it is going to be running over the surface, getting into ditches and getting into ponds. And so what these pipe networks that we design are intended to do is get water out of the street, first of all. Now, Marshall is just a perfect example of how things have sort of gone awry. And anytime it rains here, the roads are flooded. You know, when you are trying to walk from here to the main campus, you have to skip across the street. And it was a lot worse a couple of years ago when they were doing the construction here. I don't know why it was worse, but it was worse. And I went so far as to buy some pavers at Lowe's, and I'd set them down where I knew there was going to be puddles so that I'd have somewhere to step as I crossed the road. Because if you can't have good drainage, at least you can have stepping stones across the ponds in the median. So what we want to do is remove the water from the streets. Not only is it a safety issue, if just two wheels of your car get into the water, then there's a tendency for you to be steering into the water, but it also erodes the pavement, especially when there's a freeze-thaw cycle. The expanding and contraction of the standing water can be really hard on asphalt and concrete. So we want our drainage systems to get the water out of there. We need to control the rate and velocity of water in gutters. Now, in really steep areas, the water that's in a gutter can be moving fast enough to sweep small children off their feet. And so we have to put inlets close enough together that there's not a deep rush of water, like a flash flood in the street. And so it's not just a matter of intercepting the water in general, but you have to have it often enough that there's not really high velocity water, because it's a safety issue and again can scour the pavement and reduce the longevity. Now the networks are going to discharge to the natural waterways, but sometimes there's an effort made to try and clean up the water a little. And in stormwater runoff, usually where they leave it is trying to separate any kind of easily settleable solids like grit and sand. Just finding some place like in a pond, such as this, the grit will settle out, and occasionally this pond would have to be maintained, like they'd have to, after a very large event, where the water would be pooling in here and sand would be settling down. They may have to excavate the amount of sediment that had accumulated there. But then the other thing that's sometimes removed would be oil and grease. And that can be accomplished by having a skimmer on the top of the water that your pond, if you've got a pond, then the oils are going to obviously float to the top of the surface, and so the discharge from the pond would be taken from the middle where it's just the water. And so your water that's coming out had the particles settle downward, the oil and grease floated to the top, and your runoff is drawn from the middle. So that's a little bit about the control of the mass of the pollutants. Now, hopefully we can do something with these ponds that is useful other than just retaining stormwater on the very occasional times when it gets the water levels high enough to use them. Because sometimes ponds are put into place for storm events that are going to be 5 years apart or 10 years apart. And so it can seem like just nothing is happening and nothing is happening and all that land is wasted. Now it needs to be there so that a house isn't submerged every 5 years. But in the meanwhile, you want to, as much as possible, design facilities that can be used for other things as well, like parks most especially. So here in Huntington, not only are the stormwater pipes undersized, but we have different network types inside of the city limits. This is a photograph of, here's 3rd Street, here's 9th Avenue, 4th Street, and 10th Avenue. Now there's an alley that runs parallel to 9th Avenue and 10th Avenue. And down that alley, this is all of the wastewater that's being collected. So when you flush your toilet, it goes towards the wastewater treatment plant. These blue lines are stormwater networks. So it's only rainwater that's being intercepted by these pipes. And so if there was an inlet on the road, it would go in a separate stormwater network, and that's discharged directly to a creek without any treatment at the treatment plant. The problem is here in Huntington, a lot of the city is serviced by a combined sewer, meaning that the rainwater and the wastewater goes into the same pipe. So here the blue lines are representing roof drains and foundation drains that are connected to the pipe that goes to the sewer treatment plant. And that's really a problem at the treatment plant because they have the flows that they have to treat during dry weather, which is mainly people flushing their toilets and taking showers and washing dishes. But then when it's wet and rain starts to fall on roofs, and when the groundwater table rises and foundation drains kick in, then there's this runoff water as well, entering the same sewer. And so it's even more overloaded than before, and then they can have these really wet periods where the sewer backs up and it backflows into people's basements. And this is a neighborhood where that's been a problem, backflow, and the city has to send trucks out to clean up people's basements, and they've got sewage in there, and everybody's unhappy. They're trying to overcome that problem by putting in backflow preventers, which is basically like a check valve that will only allow the water to flow in one direction. Another thing they're trying to do is disconnect roof drains so that there's less demand going into these combined sewers. But legally, these people are allowed to have those old connections. They're grandfathered in because of the age of the network and the age of the homes. New construction isn't allowed to discharge rainwater into the sewer, but in the past that was allowed. And so that's one of the problems that contributes to the flooding here in Huntington is that we do have two separate networks, but a lot of the city isn't serviced by the stormwater only network. A lot of the city just relies on the combined network to take their wastewater and their stormwater both. Any questions so far? Yes?
Yeah, if you have the small piping network with problems like that, how do you resolve the problem?
It's so expensive. It's a problem that Huntington is going to have forever, is my pessimistic diagnosis, is that there's no solution because it's so expensive to replace those pipes. And to dig up the pipes, you have to replace the pavement. And the city doesn't have the money, the federal government doesn't have the money, and the harm is to the environment, and the environment doesn't vote, People vote, but usually the people who suffer the most vote the least, So I'm pessimistic that Huntington's problems are ever going to be fixed. And as it turns out, if you do disconnect these roof drains, that can help a little bit, but there's still just enough places where the rainwater makes its way into the combined sewer and where the pipes just aren't big enough that it's a very big challenge. What they like to do is they like to encourage people to use the water in their yard. And so you see how there's a green area here? You'd have the pipe going to, there's some special vegetation you can build up to try and have it infiltrate more. Instead of conveying it away quickly, you slow down the water and you have it go into the grass. We'll talk more about that because it's kind of interesting, and you can have an effect. We've done simulations here in Huntington of if you take a certain neighborhood and disconnect all of the roof drains, what effect would it have? And what it means is that these pipes will become overloaded less often. They'll still be overloaded. It just, the flooding happens a little bit less often than it otherwise would. Now we need a lot of data to do a storm sewer design. And today you're going to work an example using Excel. And some of the data that's going to go into that example is just provided. I've got a map I'm going to hand you. And all of the information that's on this list we're about to go through is on the map in the example. So I don't want us just to take for granted that it's always easy to get this information, because sometimes it's not. Sometimes it requires a survey to go out and get it. So you need to know what are the design standards when you're going to be sizing pipes. And different cities have different requirements. There are some parts of the country and different parts of the world where the standard may be a 25-year standard, meaning that flooding every 25 years is okay. And other places along interstates, for example, they have a 100-year design standard where they don't want water to accumulate by the side of the roadway, and so they design their drainage networks for interstates so that they only fail once every 100 years, or that's the intended design standard. Topographic maps of the system area. We have to know where are the drainage boundaries, what are the elevations, for example, existing storm sewers and channels so that we can not only discharge to them, but also if we're putting in a new pipe, you have to avoid crossings with water lines and other utilities. The layout of the area, like where streets are going to go and how the surface of the land is, what's the slope of the land surface. And knowing the soil type is important because some soils are incompatible with pipe materials that you may wish to use. Like if you have soils that have been contaminated with acidic contaminants, then that may cause corrosion of metal pipes, for instance. We need to know the water table levels, because if the water level is very close to the surface, then that could make a buoyant pressure push upward on plastic pipes, and those plastic pipes could potentially come through the surface. And I've got some pictures of, they sometimes have that problem when they're doing maintenance on gasoline tanks at like a gas station. When they pump them dry, and if the water level is high, then just the buoyant force of the water table pushing up on those gas tanks can cause them to break through the surface, and it almost looks like a submarine coming out of the water when they just break through. So you wouldn't think that the water levels in the aquifer or just where the water table is would have such an effect, but it does. Today we're going to look at something called an IDF curve. Anybody heard of that term before, IDF curve? No? The IDF stands for intensity, duration, frequency. You've heard of that? Okay, good. It's a characterization of rainfall, and it's a way of saying for a certain frequency of return, meaning it's going to come every 2 years or 5 years, how intense is a storm and how long does it last? And we'll look at those, and I'll show you an IDF curve, and you'll see, I think you'll get the idea very quickly from that. Now, as much as possible, we want our collection networks to be gravity flow. That means if it's gravity flow, you don't have to have pumps moving the water around. And you can really spend a lot of money on electricity pumping water from place to place. And so usually, if it can be managed, you'd like to have your entire network just flow towards the low point in the city, and then it's discharged into the lake or the river by gravity.
We have draws that the wastewater, the sewage is mostly gravity driven.
Mm-hmm.
Other networks aren't typically that way. And so there are networks that are like water distribution networks that are gravity driven.
Mm-hmm. Yeah, in fact, I used to live in Utah, which is really mountainous, and the water in Utah County is gravity flow. And so they've got the water treatment plant up on the hill, And the water being up on a hill pressurizes the network. And so there still probably are places where they have to use pumps to get water up to the top of a tower or something. But collection networks are usually gravity flow. Pipe networks where the water is being delivered into a city are less commonly gravity flow. In the mountains, yeah. And then, they must have some of the lowest costs ever, because not only was the water delivered from the mountains to the treatment plant, gravity flow, and then it went from the treatment plant into the city, gravity flow, and then they had enough slope to the lake that was nearby that the wastewater is gravity flow as well. And even some of the wastewater treatment, they were using just the static water pressure to drive. They have trickling filters that this water is spraying in a big circular tank, and they didn't have to use electricity to get it out onto the rock media. It was pretty cool. But, all right. For purposes of economy, one of the design principles that we'll follow, we're going to go through calculations to try and find the smallest pipe that's going to be acceptable. Now we have to be a little bit careful there, because they were thinking the same thing here in Huntington 100 years ago. They were thinking, well, let's use the smallest pipe because we want to save money, you know. But they weren't thinking forward into the future. They weren't thinking about how many people eventually would live in the city. They weren't thinking how much we would love to put concrete down and asphalt, because when they started putting in the pipes, it was a lot more vegetated area than it is now. And so the smallest pipe diameter that will convey flow at the design condition is maybe what I should say. Burying the pipe a certain depth below the ground surface will help to keep it warm and avoid the water inside the pipe from freezing, because nothing reduces pipe capacity more than a big gigantic piece of ice inside of your pipe network. And so we have to bury it deep enough for that, and also if it's buried too close to the surface, then cars that are passing over the pipe can transmit the load into the pipe rather than into the soil cover that's over it. There's a minimum velocity. We have to have water moving fast enough to scour the sediment that can accumulate in a drainage network. Even in a nice stormwater sewer that doesn't have human waste going through it, even just a stormwater sewer is going to have a lot of debris that gets in from the road, like litter and children's toys, and all sorts of grit is going to get in there. And so the water has to be moving fast enough to keep that stuff suspended so that it doesn't accumulate inside of the pipe. And especially during a big storm event is when those will usually get flushed out. But we have to also look out for maximum velocity, because if the water's moving too quickly, then it can erode the pipe. In the case of concrete, sort of a general rule of thumb is about 10 feet per second would be considered a maximum flow velocity, and anything above that, and you run the risk that the water is going to be moving so fast that it could erode the concrete over the long term. Now maybe this is obvious, but when you have a pipe network that's draining an area, it's considered dendritic. And what I mean by that is, so here I'm drawing on the board the river, and usually what we have is a big pipe that's discharging into the river, and then lots of little pipes that go into it. And so what you wouldn't want is you wouldn't want a pipe that's, say, a 18-inch pipe to discharge into one that's 12-inch, because that means whatever debris is making its way through the 18-inch pipe has to encounter a bigger space, not a smaller space. Otherwise, there's a much higher risk of clogging. And so a little ball sometimes would be flowing through the 18-inch pipe, and it's got to get into a bigger pipe. So the pipe should only getting larger. And beyond that, beyond the debris that may be in it, it's just you're going to be carrying more flow when you have two 18-inch pipes coming together and entering a larger trunk line, then it's going to be need to be big enough to convey all of that water. Okay, so here are some typical rules of thumb that you have to be aware of, that depending on the material type, the minimum velocity that would keep debris suspended is between 2 and 3 feet per second. Maximum velocity, depending on if it's a plastic pipe or a metal pipe. Manhole spacing is determined by wanting to have a space that you can send in cameras or people to inspect the network. And they're getting a lot more sophisticated these days with the little robots that they can send down into the pipe network with cameras to inspect and to clean. Usually we want to make sure that the manhole covers we put in match the pavement. Otherwise, if there's a depression or it's higher than the surrounding surface, then that's a safety issue. And then this minimum of 12 inches of soil cover is usually encouraged just so that it helps to distribute any kind of structural loads to the surrounding soil instead of to the pipe itself. All right. We've already seen this picture before, but I've got it up again because I want to give you kind of a conceptual overview of the rational method. This is the easiest way that we have to estimate how much water is going to come out of an area when it rains. So let's say that we're interested in a certain block within the city. This is the 4th Street and 3rd Street, 9th Avenue, and 10th Avenue. So let's say that we could measure that area and express it either in terms of square meters or in terms of acres. So we have some area of interest. In the homework assignment that I have, did I already give it to you? Yeah. I'm going to ask you to walk around in the parking lot that's to the side of the old engineering building. And sometimes the area is just as easy as roadway boundaries like this, but other times you have to identify what is the area that contributes by considering the elevation. And there may be kind of a high point in a parking lot that allows water to flow one direction versus another. And so delineating the area or trying to identify what the flow patterns are going to be sometimes is a matter of visual inspection. Sometimes if you have a topographic map that shows contour lines, you can use that. Or there's Google Earth, the program that's freely available from Google. Your cursor, as it moves over the map, it tells you the elevation. But this area, the contributing area, is just, we're saying all of the water, all of the runoff water in this area is going to be flowing to a common discharge point. So we measure a certain area and have delineated it based on looking at where are the curbs and gutters and being confident that all of the water is flowing towards the same spot that falls in this area. So when it rains onto that area, we could look at an IDF curve to find out the peak rainfall intensity. Now, the peak rainfall intensity is going to be different for different return periods. Like if we're talking about a 2-year storm, the peak rainfall intensity would be less than a 25-year storm. So the less frequent the storm, the more intense it's likely to be. And the duration of the storm also is a part of the IDF, that abbreviation: intensity, duration, frequency. Duration means that, maybe you've noticed this. If it's been the kind of day where it's just raining all day long, chances are that it wasn't like the super loud rain that you can hear in the engineering building. Like, how sometimes when it falls on that metal roof, you can actually hear it in the classroom. But it's not always like that on a rainy day. You can only hear it in the classroom for a few minutes, and then it quiets down a little bit. And that's because a really high peak intensity can only be sustained for a short duration. It's the same in nature as it is with human physical activity too. If you think about riding a bicycle or running, you can only sustain a high intensity for short bursts. And the reason for that is if you think about the rainfall, it's coming from the skies and it's coming from clouds. So it's only for a short period of time that you'd maybe have a really tall stack of clouds that are all simultaneously discharging at the same time. It may have a low intensity rainfall for a long duration, but here in this example, what we're interested in is we're interested in the rainfall intensity that coincides with something you're going to learn about at the end of class today called the time of concentration. So it's like the highest intensity that matters for this particular watershed. It happens to be how long it takes for the water to travel from one point of the watershed to another. That travel time, or the time of concentration, is what we're going to have in the back of our mind when we look at the IDF curve in a little while. But this conceptual model of runoff says that part of what determines the peak runoff is what's on the surface of the ground. If it's paved areas, more of the stormwater is going to run off than infiltrate. But if this whole area was grass and trees, then a lot of the water would just go down into the soil. And we can express how urbanized an area is by assigning a runoff coefficient, and we call that the C value. And a highly urbanized area, like a city with the streets and asphalt and roofs, maybe an industrial park like the area that's behind campus where it's just basically industrial lots and parking, may have a C value of 0.9, which means 90% of the rainfall is running off and only 10% is being used for either infiltrating into the soil or getting the surface wet. Because a fraction of the water is going to cling to wetting the surface of the ground before there's runoff. So that C value is the ratio of runoff relative to the overall quantity of rainfall that there was. And so knowing those things will allow you to estimate the peak runoff Q. And the formula to calculate Q is just Q equals CIA. So C was that unitless ratio of runoff. I is the rainfall intensity, the peak rainfall intensity, and A is the area. Now if you look at the units of that, there's kind of an odd coincidence in play. And that is, if we're working in traditional units, we'll get cubic feet per second as the flow rate by multiplying inches per hour by acres. And you can prove that to yourself by, in acres there's 43,560 square feet, and an inch is 1/12 of a foot, and then there's 3,600 seconds per hour. It turns out that actually it's 1.008 is a conversion factor that you're supposed to apply to Q equals CIA. But most of the time people don't bother with that conversion factor because C is just a guess anyway. It's kind of something that we're not very good at estimating. And this rational method only gives you kind of a basic understanding of the peak flow. It's not super accurate. I mean, it's pretty good. It's worth taking the time to calculate what the rational method predicts as the runoff for an area. But this is certainly not sophisticated. No one's going to be impressed that you did a rational method analysis. It's the kind of estimate that you can spend 5 or 10 minutes to put together and it will be informative but not comprehensive. So it's really simple and it's conservative, meaning it overestimates usually. It would be even worse if it wasn't that accurate and it consistently underestimated the peak flow. But when you calculate the runoff using this, at least you can be comfortable that you're not going to underestimate, that the value it gives you is going to probably be too high. And so if you do your design based on Q equals CIA, you'll probably be safe. The pipe will probably be bigger than it needs to be rather than smaller. It should only be used for relatively small catchments, less than 80 hectares, and the minimum time of concentration is 5 minutes. because that's what you need to get the intensity of the rainfall off of most IDF curves. There are a few assumptions that are in the background when you use that. And part of why it's a little bit inaccurate is the fact that reality doesn't follow these assumptions. In reality, for instance, when it starts to rain, it's not the same intensity through the whole storm. And if you look outside, you can see sometimes it's raining hard, sometimes it's not raining hard, and so intensity of a real storm is variable. But this Q equals CIA method is assuming that the rainfall intensity is constant. The method that we'll follow in applying the rational method is, first of all, we have to estimate or calculate a time of concentration. And just conceptually, the time of concentration is when I was talking about how long does it take for water at the furthest boundaries of the watershed to get towards the outlet. And the outlet is just the point that all of the water seems to be draining to. And so if all of the water was going to this point in the watershed, we'd look at, where's the furthest journey that water is taking. Maybe the water has to flow along this sidewalk, get into the alley, and then flow down the alley till it finally gets to there. And so we'd find that distance and estimate the time that it takes. There are some formulas we can use to estimate the time. The easiest approach is just to say, well, when it's going on this asphalt, it's moving maybe 1 foot per second, and then it gets into a gutter and it's going 2 feet per second. Just using the distance and the speed to estimate the time. So estimating how long that time is, and then with that time you go to the intensity, duration, frequency curve to find the I, the intensity, and then assessing the land characteristics to determine the C value, and then you plug the numbers in. Q equals CIA, and solve for the Q, the peak runoff flow rate. Questions about that? Okay, here's a table that comes from your text. It shows some typical C values for different types of surfaces, for developed areas where it's concrete surface or roofs, grassy areas, pastures, forests or woods, and so on. What's interesting to look at is that there's different columns for different return periods. So let me ask you this. Why do you think that there's a different C value for a 5-year storm compared to a 50-year storm? And you'll notice the C value is going up. So what they're saying is that if you only have a 5-year storm, 80% of the water will run off in a 5-year storm. But in a 50-year storm, 92% of the water is going to run off. Okay? So in the shorter, smaller storm, in this small storm, a greater fraction of the water is used up in saturating the ground or wetting the surface as compared to in the larger storm, there's more water, and so a smaller fraction of it is going to be used to satisfy, that's called initial abstraction, like when you're doing surface wetting, and it's what has to get wet before the water can really start to move. Did you have a comment that you were going to add? Okay, all right. Another part of it is just that the 50-year storm is more intense. And so when you've got a greater intensity, then maybe it's not just the quantity of water, but the water is like rushing over the surface more quickly, and so it's spending less time. There's less time for it to saturate downward. Okay, so that's talking about the trend we saw as we looked through the columns. Now look at the effect of slope. Let's consider grass, a fair condition grass, meaning grass covers 50 to 75% of the area. That sounds like my yard, where about 50% of the area is just like dead patches, And then about 50% of the area is like okay grass. And so a fair conditioned lawn. Why is it that a steep grass has a different C value than flat grass? It's saying 34% of the water will run off for a flat grassy area, but more of it's going to run off if it's steep. Why? So if it's flat, there's pooling, yeah, and then if you've got a pool of water, that's more of a driving force to get the water infiltrating. But if it's sloped, then it's already moving, it's got momentum, there's less of a tendency for it to infiltrate down into the soil. So that's the other trend we need to be aware of, is that steep areas tend towards less infiltration and more runoff. And so what do we have here in West Virginia? We've got very steep areas. 7%, no, we'll laugh at a 7% slope in West Virginia. I've got 40 and 50% slope watershed areas that sometimes I do models of. And so, you know, they're considered very flashy watersheds because when it rains, the peak comes through very quickly. Okay, so this is a nice resource in your text of C values for different conditions. Let's try out this example here. We have a 5-year, 24-hour storm. Now there's two different times that are listed here. One is the duration and one is the frequency. Which is which? Right. Perfect. That's right. Yeah. So the rainfall itself is lasting for 24 hours. 5 years is the return period or the frequency. The peak rainfall intensity is 95 millimeters per hour. Now here, the peak, basically that means we've already looked at the IDF table and found the rainfall intensity that corresponds to the time of concentration that we feel like applies. Okay, so that's the I. No, see, I want to use these. I want to try and use these, but every time I do, I'm disappointed. I can just never get these to work. I'm cursed. I'll ask Dr. Michelson if he can help me out. All right, I'll just do it on the whiteboard for now. Our viewers at home will have to imagine. Okay, so try this out. We've got I is 95 millimeters per hour. So we're going to have to convert that into, if we want meters per second as the Q, we're going to have to convert that into how many meters per second is that. The catchment consists of 4 hectares of parking, 12 hectares of fair lawns and a 4% slope, a 4-hectare rail yard, and 18 hectares of single-family housing. So what we need to do there is find a composite C value. If I go back to the previous table, I'm not showing the one that has all the rail yard information. In your book, it has that. All right. For the parking, let's find out what C value corresponds to asphaltic here, or concrete. Yeah, for a 5-year storm, it's saying 0.77. Okay, so let's have 4 hectares of C equals 0.77, and then 12 hectares of fair lawns with 4% slope. So 12 hectares, our C value for a fair lawn, 4% slope, and the 5-year storm, it's 0.36. Okay, so 0.36. That watershed also has 4 hectares of a rail yard. Now, I'm just guessing that the rail yard has a C value of 0.6. And what is that based on? Well, let's say maybe it's partly dirt, it's partly like rocks, you know, the ballast that they have near the rail lines itself. On the one end, if it was all concrete or roof, it would be 0.8. So it's not that bad, but it's not grass either. It's not even as good as like a poor grass. And so this 0.6 is just, you can call it a guess. If we wanted to put a nice spin on it, we could call it engineering judgment. But 18 hectares is housing. And again, that's a guess, and I'm just going to say that housing is partly grassy areas, but it's also partly roof area. And so if we did an average, a lot that's maybe half roof and half grass around the yard, then maybe a good middle ground would be 0.5 for that. And so we can do a composite, which is a weighted average. So our average C value is just going to be multiply the 4 hectares by 0.77, 12 times 0.36, and then we're going to divide by the sum of the areas. So 4 times 0.77, 12 times 0.36, 4 hectares of 0.60, and 18 hectares of 0.5. Dividing all of that by the sum total of the areas, which is 38 hectares. So the average C value for this area is going to be 0.495 if we want to come up with like a weighted C. So the C value of 0.495 is just saying the average C value for all of that. Okay, so we want to have Q equals CIA tell us the flow rate in terms of cubic meters per second. Rather than calculate this intensity to meters per second, I think what I'll do is I'll say that 95 millimeters per hour is 0.095 meters per hour. So that when I substitute in Q equals CIA, I'm going to have this average C value of 0.495, the intensity of 0.095 meters per hour, and then our area, the overall 38 hectares. By the way, if you're not already acquainted, 1 hectare is 10,000 square meters. Okay, so we've got 10,000 square meters times 38 is our area here. So 38 times 10,000, and that's meters squared. Anybody calculate that and tell us what will be the cubic meters per hour runoff for this watershed? $17,869 cubic meters per second. Oh, per hour, right? Per hour. So if we now divide that by 3,600, then it's about 4.96 cubic meters per second. So it's just a really quick and easy way to figure out the peak runoff from an area. And keep in mind that this is a conservative estimate. And so the actual peak runoff is probably a little bit lower. Any questions? Okay, let's take a little break. I'm going to go get a couple of the laptops that we've got available. We need 2, right? All right. I'll bring back 2, and then when we get back together in 5 or so minutes, we're going to do an example on how to size pipe networks using Excel. I'm going to give you a map. That's the same thing that's on the screen here. Okay, we have an area that is being developed, and we want to know how big the pipes should be in that area. And we've got an idea of the land elevations. That's what these dashed curved lines are. This is the contour lines represent the land surface. Here you can see that there are some roads and so on. And the naming system for the pipe networks and the catchments is that they have 1.1 is the first inlet. So all of the water in a certain area is going into inlet 1.1. And the area that contributes to 1.1 is this area. So it's the outside boundary and then this dashed line. So all of that area is contributing to inlet 1.1. So if you want to look here at 1.2, it's this contributing area. All of the water that runs off from that boundary goes into 1.2. And both of those inlets feed to pipes, and those pipes come together at junction 2.1, and there's also water coming in at 2.1 from the land area that is defined by this area. So it's a big one. The area that contributes to 2.1 is a pretty large contributing area. Now there's a lot of dashed lines here. Some of them are representing streets, but the boundaries of the watershed is what we're interested in. So what we're going to go through in the example today is, first of all, we're going to, with the given areas, the handout that I've just given you, let me put that on the screen for those who are watching at home or from the hospital. I guess it's home at this point. All right. Okay, so this is the handout that I've just given everyone. And it's got an IDF curve on it, just for the, I think this IDF curve corresponds to the 25-year storm. So what it's showing is that for a certain duration, there's going to be a different rainfall intensity. And so some of the points taken from this curve is that if the storm duration is just I just honestly couldn't care less. All these questions it asks me. Where's that box? I couldn't care less. All right, so 5-minute duration corresponds to a high intensity, 5.4 inches per hour. 10-minute storm duration, we go over here and it corresponds to 4.2 inches per hour and so on. So there's a website that I'm going to show you later in the semester where you can click on any location in the United States and it will give you data like this. It will give you data on, for the duration of the storm, what's the intensity of the storm. Here's also some data. I've already done the area measurements, and so we have the area in acres. We have a C value for each of these areas, and then the time of concentration is corresponding to how long it takes the water to travel over the surface of the land until it intercepts that catchment. Okay, so does the interpretation of this figure and the table make sense to everybody? Any questions about that? On the IDF curve? And that's a good question. I think it is linear. Yeah, it's just maybe a sloppy scan or something. It's certainly not logarithmic, right? Yeah. It would be more distorted if it was logarithmic. Okay, so what we want to do is basically find out how big should pipe A, B, and C. How big do those pipes need to be? And so the process that we're going to go through is that you need to fill in some information. I'm going to give you a template because you've never seen anything like this before necessarily, so I don't want to just throw you right into the project without a little bit of assistance. So the template that you should use, is that the one that's already open? Okay, here's the template. There's a whole process here, and once you get the paper filled in with some of the beginning information, then we'll actually go to Excel, and using this as a starting point, see if we can calculate the needed pipe diameter. Now, this is going to use Manning's equation, and everyone probably remembers Manning's equation from hydraulic engineering, or maybe even fluid mechanics. The formula that's at the bottom here for the diameter required, that's just rearranging Manning's equation to say what size of pipe should go there. All right, so what I'd like you to take some time to fill in is we have pipe A, B, and C. The length is already defined for you. The slope of the pipe is based on the ground elevations, and so we have this map here. And so if you look at the slopes that are on that handout that I just gave you, it's based roughly on matching the ground slope. Now the pipe doesn't have to be the same as the ground slope because the pipe isn't at the surface, the pipe is buried. And there is a degree of independence between the pipe slope and the ground slope, but if you make the pipe really steep for a long time, then that means it's going to be getting deeper and deeper below the surface. And so over the long run, the pipe slope and the ground slope have to either match, or you have to lift the water back up again with intermediate pumps occasionally. All right, so back to this one. I'd like you to name the junctions, try and follow the same naming scheme that's before. We have the area in acres, the C value, and so what we're going to do in Excel is have it do these calculations of the area times the C value, and that'll give us CA. And then the sum of CA is going to be where we have to start applying a little bit of interpretation. So what you should do is, on the handout I've just given you, fill in the blanks on the actual paper with the junction numbering, and then take some time to set up Excel following these same titles. You know, put the same column titles in. So have a column named pipe name, have a column named length, add each one of these columns to a blank spreadsheet, and then we're going to go through together the calculations that show how you can find out the diameter that the pipes should actually be. So pipe A, I think you've already filled in the information. The upstream of pipe A is 1.1, downstream is 2.1. For pipe B, it is 1.2 goes to 2.1. And then pipe C, it is upstream is the 2.1 end, and the downstream is the 3.1 end. All right. If you've got the areas and the C values for those three contributing areas, then C times A is just going to be C times A. Easy enough that way. Multiply the two together, and then you can drag the formula down so that it applies it to all three rows. Okay. Zoom in a little bit there. Now, some of the columns, like this sum of the CA, it really only makes sense if you're designing a big area. And let me show you the full map. What you have on your handout is much smaller than the actual full system. Like, for purposes of making this example a little bit shorter than it usually is, here's the full map. It's a lot of pipes. And so I've abbreviated this example, and we're just looking at one section of the example. So what I'm saying is that when you get down into some of these pipes downstream, that's when some of the columns, like this second T sub D column, it really makes it's the most important when you get a little bit deeper into the network. All right. But for now, the sum of the CA is for this one. It's for pipe A. If you look at what's flowing through, let's see. I'm going to copy and paste this to here. Okay. Crop it. We only have to here, right? All right. So look at what's in pipe A. Pipe A only gets water from this one inlet, 1.1. So the sum of the CAs is just 1.43. And the same thing is true for pipe B, which is this one that goes from 1.2 to 2.1. It only has the CA of that one. But pipe C, as it's called on the handout I've given you, it has water from 3 different ones. Yeah, it's got not only this area contributing to it, but it's got these 2 areas as well, because there's a total of 3 openings feeding water into pipe C. And so for the sum of the CAs, we should say equals sum, and then add up all of these CAs, because all 3 of those inlets is contributing water into pipe C. Does that make sense? Dynamite. All right. Now, this upstream time to inlet is the travel time, how long it takes for water to flow over the surface until it gets into the inlet. And so that was just given immediately. There's not anything that you need to do with that yet. And it's overland flow, meaning that it was over the surface of the land to get into that inlet. And this column, time to flow, upstream flow time, that is one that kicks in when we're talking about other pipes downstream of the network. And so it's 0 at this point just because it doesn't apply yet for pipes A, B, or C. So the time of concentration is the same as the T sub D for these first 3 inlets. So you can just have it select the T sub D, T sub C, and the T sub D is equal. And the same thing is true here. It's just equal to what it was before. The intensity is information from that IDF curve. So from here, the intensity that we're using is we're interpolating a little bit based on these data points. And so if we have 11 minutes, then we're saying 4 inches per hour based on 11 minutes. And let's see if that makes sense. 10 minutes was going to be 4.2 inches per hour. So it's going to be a little bit lower than that. It looks like 11 minutes is where the IDF curve crosses 4. And so for 9.2 minutes, this is the intensity that goes with that. 13 minutes, it should be even a little bit lower than 4 inches per hour. So I was just going from the figure, looking at the curve, and trying to relate certain durations to the rainfall intensities that go with it. Okay. Now the Q, this is where we're using Q equals CIA. And so we should have Q equals, the C and the A are together here, so you can just click on that sum of CA and then multiply it by the intensity. And so 5.72 CFS is just based on the contributing area, the runoff coefficient, and the intensity. And the same thing is true for the water that's getting into inlet 1.2. And then the 18.84 that's getting into pipe C. So this is the peak. Now, the diameter required, we're using this formula. This is Manning's equation rearranged. And so we have to type that in kind of carefully in Excel here. The formula for that is the MD that it says here is based on the units. We're working in BG units, so we're going to use 2.16 for the M sub D. Okay, so I'm going to have a parentheses then 2.16 times the Q, which is this peak flow rate, times the N value. And the pipe material that we're using here is concrete with an N value of 0.014. That's what this cell is the N value. So I'll just times and click there. Divided by the square root of the slope of the pipe. And the slope of the pipe is given right here. So the square root of the slope. And then we close that parentheses, and it's all to the power of 3/8. So that tells us that the exact pipe size requirement is 1.08 feet. But they don't make pipes that are exactly that diameter. They make pipes in increments. You know, there would be a 1 foot diameter sizing, then maybe the next size up from that would be 1.25 feet in diameter. And so here for the nominal size that I'm putting of 1.25, you'd have to just sort of have an idea of what pipe sizes are available. I'm going to assume that they come, in this case, the next step up besides 1.08 would be 1.25. And so if the pipe is, that's the size, then for the flow velocity, it says here in the instructions that what you can do is use Q equals VA. And so we have the Q. You can calculate the area based on this diameter and then find the velocity. And so Q equal, the velocity is Q divided by the area. And so the area of the pipe is pi d squared divided by 4. So pi times d, which is this nominal design diameter, d squared divided by 4. And that says the water is flowing at 4.66 feet per second. And then this flow time column is saying if we have a pipe that's 390 feet long, then how many minutes does it take for it to travel through a pipe of that length when this is the flow velocity? So that's going to be the length of the pipe divided by the velocity. And then that will tell us how many seconds it is. And so we need to convert from seconds to minutes by dividing by 60. So it's 1.39 minutes is the travel time as the water, that's the travel time that the water experiences going from 1.1 until it gets to junction 1.2. And the reason why we had to calculate that travel time is that I'm going to take that travel time and I'm going to put it into this spot here. The 1.4 that's listed there is based on the flow time upstream, because I know it takes 1.39 minutes because there's a lot going on at this junction 2.1. Not only is there the water flowing over the surface, but there's also water coming in from pipe B and water coming in from pipe A. And how big pipe, what are we calling it, pipe C? The size of pipe C depends on not only the water that's coming over the surface, but also the water that came in at this junction and the delay time. Because the travel time in pipe A and the travel time in pipe B has an effect on the size that's required for pipe C. And so that's why over here I'm going to include the 1.39 there, and so I can take that same formula and apply it down to these other ones. Oop, looks like I didn't anchor something that I should have. Yeah. All right, so I'm going to push the F4 button. That'll add the anchors in. All right. So if I drag that down now, I've got some sizes, and then the next largest size would be maybe 1.50. And if it's 1.62, let's say the next largest is 1.75. And so then I can get both the flow velocities and the travel times for both of those. All right, and I'm going to enter in this 1.31 was the delay time from when the water enters pipe B to when it gets to the end of pipe B. Now this time to inlet is from 1.1, it is 11 minutes and 9.2 minutes, because that's how long it was of the overland flow. So the total time of concentration is going to be the overland flow time and the upstream flow time. That's basically what we're talking about, is how long does it take for the water from this watershed to get to junction 2.1. So it takes the amount of time that it was flowing over the surface and then the amount of time it was flowing through the pipe. And so that's why we have this T sub C calculation, and then the longest of the three is what we would put in the T sub D column here. So it's 13.7 because the longest of those three possibilities is what governs. Now, that becomes more important when we have a more lengthy network. Like if it was that whole, like this entire network, then we'd have to pay really close attention. But since this is an abbreviated one and your homework is also a relatively simple network, then it ends up not being, example, not being quite as critical. These ones? All right. It's because so far we don't have any travel times accounted for yet. It's just overland flow. But now you notice that these T's aren't the same. These T sub C's, because this 11 minutes is just the time it takes to flow over the land to get into inlet 1.1. But then if you add the pipe travel time of 1.39 minutes, that's where this comes from. Now, this T sub D is going to be the one that governs what intensity you should use. And there's three possibilities for junction 2.1, like which time of concentration to use could depend on, let me make the image a little bit larger. All right. Think about how the water is getting into pipe C. The water can get into pipe C from three different locations. It can get in that pipe through this inlet, through that one, or this one. So we have to say, you know, what's the longest travel time that it could take? You know, like maybe a raindrop falls here in this corner, and it flows over the surface, and then it gets in the pipe, and now it's about to enter pipe C. So how long did it take? And we could measure that in minutes. Or maybe it was some water that traveled over the surface from this corner, and it's taking a long time because it's a long transit. It's having to go, and finally it gets into the inlet, and now it's about to flow through the pipe. Or it could have been the water here. It enters the inlet and goes through the pipe. And so there's three different possible times of concentration, and we have to calculate all three before we know which is the lengthiest. So that's what these three numbers are representing, is like the maximum flow time for each of the three paths that water is taking in order to get into pipe C. And this column T sub D is the longest of all the possible routes. So maybe it actually becomes a little bit simpler when I show you the full solution, because the full solution has other network elements as well. So let's see what happens when we get into the next group of pipes. Like here is A, B, C. But now what I'm calling D and E is, here's pipe D, and here's pipe E. And then what you'll notice is that for each one of these different spurs on the network, we have to calculate the contributing areas. We have to look at whether the water is flowing over the land or through the pipe network. And if it's through the pipe network, the times are sort of a lot longer, because it's not only the overland flow time, but then it's also the transit time, the cumulative transit time that it takes. So you'll notice that the pipes get progressively larger and larger and larger. So this is the trunk line here that started at 1.75, then the next segment is 2, then the next segment is 3. But it definitely, the first time you look at it is tricky. I think what I hope will help you is these definitions. When you are going through this again later as you're preparing for the homework assignment, I hope that the structure in the handout I've given you and these row explanations will be enough to allow you to calculate the problems. And if you look at the handout I've given you for the assignment, the first problem is just 2 pipes. The next one, there are 3 pipes. So it's actually, the network is about the same in complexity as what you're looking at for the example. And if you think this is confusing, then open up the book and see how they explained it. I promise you it's even worse. So, all right. Well, that's a great question. The times don't keep building because what we're doing is we're seeing the water travels very quickly through the pipes. Like once it gets into the pipe, it's only a matter of, the travel time is less than a minute usually. And so it's getting bigger, but not a lot bigger compared to the overland flow times. Like when you've got 13 minutes of overland flow, but then only 0.4 minutes of travel through the pipe, then the time that the water's spending in the pipe network ends up being not negligible, but a much smaller component. So this 14 is based on the travel time from the previous iteration. You're choosing the biggest of all the possible routes that the water could have taken. Now, we just we were given the overland flow times in the example, but what we're talking about, it's called Hortonian overland flow. And what happens is if the precipitation rate is greater than the soil's capacity to absorb water, then there will be what's called an excess, a rainfall excess, if the rainfall capacity exceeds the infiltration capacity. And so water starts to pond, and if there's a slope to the surface, then the water will start to flow. And there are many different empirical formulas that have been developed that try to predict what the time of travel is going to be. And one of them is called the kinematic wave. And the kinematic wave only has limited applicability because The distances that it's applicable over are about 100 meters of length. But if you look at what factors go into the formula here, they're saying how long it's going to take for the water to travel over a certain distance. Obviously, the time of travel partly is dependent on how long the distance is. So that's what L is. But they're also saying that the roughness of the surface plays a role. And so the N value here is the Manning's roughness coefficient. And the rougher the surface is, the more the transit time is going to be. And so if it's a smooth surface, the water can flow very quickly. If it's a rough surface, that slows it down and increases the time it takes. In the denominator here is the rainfall intensity and the slope. So can you think of a reason why those would be in the denominator of the equation? Like, why would a higher slope be in the denominator when it comes to the time of concentration? So big slope means smaller time of concentration. Why? It's going to have a higher speed. It will run off more quickly. And the same thing is true of rainfall intensity. It's the same trend we were talking about earlier when we were looking at the C values. But if you have a high rainfall intensity, then that's going to decrease the time of concentration because the water's moving quickly. All right. Now, what makes this a little bit unique is that you have to know the time of concentration in order to get the rainfall intensity, but you need the rainfall intensity in order to get the time of concentration. And so you have to kind of, it's called a trial and error approach. It's iterative because you don't know the T sub C until you know the I and vice versa. But you can, by going back, you'd make some guess value of the T sub C the first time so that you can find out a rainfall intensity, and then you check that guess value to see if it's valid and make adjustments if necessary. So this is considered maybe the most sophisticated of the options for calculating the time of concentration. All of the other methods don't have as many parameters, and so they're not being as sensitive to differences in rainfall or differences in slope. Here are some N values that you can use for overland flow. And the table of N values that you used for culverts was different than this because you had a greater depth of flow, the water that's going over the channel downstream of a culvert. These are usually relatively shallow concentrations of flow. I mean, a rainfall on the surface, then if it gets any deeper than a centimeter, then you don't have overland flow anymore. You'd have what's called shallow concentrated flow, or you'd have channelized flow. But here are the N values that go for overland flow and different types of grass even. They've distinguished between whether it's natural or clipped range and so on, bluegrass sod. Bermuda grass, yeah. Very rough, very high roughness on Bermuda grass. The NRCS method is accounting for some of the same factors. You'll notice that, again, the length is one of the parameters, as is the roughness. But now you're not using the rainfall intensity anymore. You're using something related to it, though. Rather than having the actual rainfall intensity for the storm that you're interested in, this NRCS equation says let's just put in the rainfall depth for the typical 2-year, 24-hour storm in this area, the area of interest. And so it's not going to be sensitive from one storm to the other in your location of interest, but at least it will distinguish between maybe the rainfall patterns in West Virginia compared to rainfall patterns in North Dakota, you know, whatever the P sub 2 is. Mm-hmm. Yes. Mm-hmm. There is. And in fact, that's some of the research that I've been doing lately. And the way that you measure it is you set up a rain gauge and you also set up a stream gauge. And both of them have very sensitive clocks. And so the rain gauge, when it starts to sense that actually precipitation is beginning, it measures with a tip every time a certain amount of rainfall occurs, and the sensor knows when it's raining, and the stream gauge that's in the river knows when the water starts to rise, like when the stream is getting deeper. And so then after the fact, what you can do is you can download the data and just look at when did it rain compared to when did the river get deeper. And the difference between the two is the time of concentration. And so that's a physical measurement of it. You can also physically measure, like in a parking lot, if you pour a dye, like a visible dye, like some red food coloring. You yell to your friend, okay, release the food coloring, and then you're standing at the drain. And when you can see that dye, like when it's visible, or there are ultraviolet dyes that you can use, equipment that would sense it, and so people aren't being disturbed by blood running through the streets or whatever. And so like you're physically looking for some sort of a tracer, as it's called. So those would be two ways of physically measuring it. And that's how these equations were developed, is they went out into the field and they did some studies under a range of conditions. They measured how long it took for the water to travel, and they said, wow, this is so inconvenient. People don't want to have to do this physical measurement everywhere they go. So let's just make these equations to try and act as a rule of thumb in other places. Slope is also there for the same reasons that we talked about before. The Kirpich equation is used in larger watersheds than either of the other two that we've talked about. The other two that we've been talking about have been limited to distances of about 100 meters. But for the Kirpich equation, you can use watersheds up to 80 hectare in size. And so that's getting pretty big. Unfortunately, it's not really sensitive to the material type. N value isn't in the formula. And instead, they just have these rough multipliers they recommend that, for example, if you have a concrete channel, do your calculations and then multiply it by 0.2. So that means that it's actually going to be a lot faster than you calculated with your T sub C formula. But if it was a grass channel, like a canal that has grass lining, presumably that would retard the flow a little bit because of the resistance of the grass, then you'd have double the time of concentration.
The difference between the top and the concrete channel, this is a channel, this is not a street.
Yeah, overland flow versus channelized flow. And I'm glad you asked that, because I used those terms a moment ago, but I didn't really distinguish among them very well. And so let me do that now. Let me do a little sketch that I hope will illustrate the difference. So there's overland flow. Sometimes we would also call it sheet flow. So think about if you have a rain coming down and it's falling onto a surface and it's flowing everywhere evenly. Like it's not grouping together yet. So here is overland flow, and it stays like the flow is as a sheet. It's kind of evenly flowing over the surface. But now, if there happens to be a little bit of a depression, like all of a sudden you notice it's all kind of going together, and now it's kind of pooling together, but it's still relatively shallow, then this section would maybe be called shallow concentrated flow. And you'll see that in the parking lot if it's raining on the day when you go out to do that part of the assignment. Like in the parking lot, there will be some places where it's just more of the water has come together in a single spot, and it's not like it's a channel or anything, but it's just what the name describes. It's shallow, but it's concentrated flow, where several different of these streamlines have come together and it's flowing. And then The last among them, channelized flow, would be like a stream, a creek, or a gutter, where it's clearly intended to move the water from one place to another. And it's going to be deeper than maybe 1 centimeter. So if we were looking for like thresholds, probably overland flow is maybe just a few millimeters. Any more than a few millimeters and it's going to naturally become shallow concentrated. And so shallow concentrated is from, so we'll say up to a few millimeters. Shallow concentrated flow is from a few millimeters to maybe 1 or 2 centimeters. And then channelized flow is going to be more than 1 to 2 centimeters. So like channel flow would be a gutter. And why do we bother distinguishing between these 3 different flow types? It's because the more shallow it is, it's moving very slowly, because there's a lot of resistance to flow as water is moving over the surface of concrete. That concrete is applying a high shear stress, and so the water doesn't move very quickly as it's flowing on sheet flow. But then when it channelizes and it gets more depth to it, then it can flow more freely and with a much higher velocity. And so we distinguish between these kinds of flow because of the speed that they entail. And when we're talking about time of concentration, so the difference between overland flow on concrete and concrete channel, the travel time is going to be less in a concrete channel because the speed is higher. So I'm glad you asked that question. There is a difference between these 2 bullet points. Are there other questions? Okay, so here's another formula type called IZARD. Again, we do have effective rainfall intensity, and there's length that's being accounted for. But now, instead of N value, they have their own special measure of roughness that they're calling the retardance coefficient. And the retardance coefficient is calculated based on this formula for the K value, the rainfall intensity, the slope, and the C sub r that varies on different types of surfaces. It was used on a lot of grassy areas. It wasn't used for much channelized flow. If you look at the different types of materials, they're talking about grass and pavements. The Kirby equation is used for small watersheds, small catchments. This could be used for like parking lots or like house-sized developments. There's a lot of options out there, and they're summarized in the book. Just to give you an idea of the huge range of variations, let's try some of these equations for the same area. We'll see if we can translate them into being applied to kinematic wave, NRCS, Kerr-Pitch, IZARD, and Kirby. All right. All right, so first one, kinematic wave. Formula for kinematic wave, T sub C is 6.99 N times L to the 0.6 power. Intensity to the 0.4 power, and then slope to 0.3. We know here that the slope is 0.015. The distance that we are going to be working with, the length here, L, is 75 meters. The effective rainfall rate, the I that we're going to use, is 45 millimeters per hour. And then the N value for a grassy area, we'll use N is 0.15 from the tables that we looked at before. So what I'd like you to do is substitute that into, this first one is kinematic wave. And I'll put the formula also for NRCS, Kirpich, Izzard, and Kirby. And we'll find out how these times compare. So let me draw those other equations on the board there. All right, so for kinematic wave, has anybody already finished the calculations and got around 23 minutes for that? Okay. So we can think of the kinematic wave as being maybe the best one that we've got under these circumstances, because the distance is within the 100-meter limit for kinematic wave, and the kinematic wave is the one that has the best expression of rainfall intensity built into the equation. So around 23 minutes is maybe the most appropriate. The other guesses don't fare quite as well. And the NRCS method, we had to calculate a precipitation depth. And so here I converted an intensity to a depth by multiplying by the duration of the storm, which is 20 minutes, or 1/3 of an hour. So that's 15 millimeters or 1.5 cm. And you wouldn't know it, but the units that need to go in here for the precipitation depth should be centimeters, the way that they've got this equation formatted. And the time that it gives you is in terms of hours. Does it say the units? I don't remember if I, hopefully, okay. Yeah, so rainfall in cm, travel time in hours. So when we do that, it turns out to be quite a bit longer than our guess of 23 minutes. And probably the weakness here is in the precipitation depth. And part of the reason for that is that what we're supposed to be putting in there is a 2-year, 24-hour storm. But the storm that we had in the problem statement, it said in the example, we're doing it for a 20-minute storm rather than for a 24-hour storm. So it's maybe a little bit unfair, and we probably would have gotten better results if we had somehow extrapolated a precipitation depth a little bit larger than that what we did. Okay, so for the Kirpich equation, if we substitute in 75 meters and then the slope of 0.015, then we have to double it for overland flow, that times 2 multiplier. It's only 5.3 minutes. And so it's, the Kirpich equation like really struck out in this case. And if we go back to looking at the criteria, like what are the limitations of the Kirpich equation, well, the reason why it didn't do so good is it's for much larger watersheds than this example. Like the example is talking about a 75-meter length, but the Kirpich equation was constructed for watersheds up to 80 hectares in size. And so it's naturally biased to calculating small times of calculation. And so that's why this one is a lot smaller than the others is, because we're working outside of the intended range. Okay. Now, Izzard, we had to first calculate the retardance coefficient and then the K value based on the retardance coefficient. So table 5.19 for the, let's see, where was that? Okay, yeah, so the 0.046 5.19. I was saying it's a mix of the grasses, because in the problem statement, we don't really know here what kind of grass it is. It just says a grassy area. So what I did was I said, well, here's closely clipped sod and here's dense bluegrass, and I did some average between them in my estimate of using Izzard. And so I said, let's use an average C sub R of about 0.053, and then that is what I put into this formula to calculate the K value, using the same 45 millimeters per hour for the intensity and the slope. So then with that K value of 0.21, then the time that was calculated is about 38 minutes. And so we're back in maybe the reasonable range again. It's not giving us wild guesses like 5 minutes for the Izzard. But then Kirby ended up being a little bit on the low side again. So which formula to use is in some cases a matter of personal preference, but it's largely driven by the regulatory climate. And for example, there are drainage manuals for each state that's put out by the Division of Highways in the state that you're working in, and so they have their preferences specified. And in my case, I use the NRCS method whenever possible. I'd like to use kinematic wave, but you're limited on the distances. When we go into watershed modeling, there are a few other methods that are used for large watersheds besides the Kirpich equation. There's a lot of different possibilities, but the final homework assignment problem that you've got that's due next week is I'm asking you to do some calculations related to time of concentration for the parking lot outside the building. And there's a picture on the third page that I've drawn an arrow that indicates where there was an inlet. I think that inlet's still there. I don't think they've repaved that parking lot since I originally created this assignment. And I also have the intensity, duration, frequency table for Huntington. And so it's got these numbers, the 4.26, that's inches per hour for a 1-year storm that has a duration of 5 minutes. So the units aren't written there, but those are inches per hour.